Hey y'all, this is our Electrical Engineering 201 lab final project at South Carolina. I'm Dean Phillip.
I'm Corey Schmidt.
I'm Wayne Gregory.
The objective of our project was to implement an FPGA board to create a system that received inputs and gave us the desired outputs.
So we use this with a FPGA, which is a field programmable gate array. It uses logic gates in conjunction with one another to decide outputs. This is used with parallel processing, unlike a microcontroller. A microcontroller works sequentially, so it decides an output from inputs. With this logic gate, it does it one at a time, so it does one logic gate, then another. Or an FPGA, where if they're all lined up parallel with each other, you can do all of them at once. So it takes delta K time for an FPGA to do, let's say, 6 logic gates, whereas a microcontroller, it'll take 6 times the amount of time because there are 6 logic gates and it has to go one by one for each one.
So practical purposes of an FPGA in the real world can be any problem that can be computationally done. Some examples are digital signal processing, embedded imaging, and many other growing fields.
So our project was broken down into 3 subsystems. The first was very simple. It was just 4 push buttons, which gave digital inputs to the FPGA board, which gave us the options between 0 and 15, so 16 total input options to work with. We took those input options and created a truth table, which can be used to decide what the outputs are going to be. And then based on our truth table, we used K-mapping to simplify the statements so that we could we could put it into the FPGA program much more simply.
So System 2 consisted of the FPGA Mojo board. The programming language for the board is FHDL, which is Visual Very High Speed Very Hardware Description Language. It's a general program parallel processing program. There are 2 methods for VHDL. One is conventional for higher level languages. The other is schematic. We use schematic 2 points that are behooved. For schematic is designed to be described at various levels of abstraction, and functionality simulation is easy and only design flow. The input output on the board is a control user that can be programmed to be inputs, outputs, or bidirectional.
So our third subsystem is essentially an inverter with a 7-segment display. We're using NOT gates in this IC, which is an inverter, going into the 7-segment display, which is a common cathode 7-segment display, which means that the endpoint is common between all the diodes. So we grounded that, and all the inputs are now coming from the inverter. So when the one coming out of the Mojo board goes into the inverter, it's now 0. So the 0 going into the LED makes the LED not light up. So the LED will only light up when the board is outputting 0s. So this is helpful because the LED will then light up in the 7-segment display when the inverter is giving it power rather than the power coming from the board, which makes it easier or better for the board because it's not, it doesn't have a lot of current flow out of it when the LED is on. The next thing we have is the materials. The materials needed are a micro USB to USB cable, Mojo version 3 FPGA board with a Spartan 6 chip, 4 momentary push buttons, 4 10K resistors, 2 HD74 LS04P ICs, which are the NOT gates, 1 common cathode 7-segment display, 1K resistors, but 14 of them, miscellaneous wire connections, a laptop or computer with USB 2.0 or later, Mojo loader and ISE Project Navigator loaded on them, 1 LED, and a power supply.
So this procedure for subsystem 2, the team started out by researching FPGAs on the company website, embeddedprocessors.com, I think it is. The program is VHDL. We did that to get a general sense of the programming language and how FPGAs work and the possibilities of what FPGA can do. We did the LED onboard tutorial, which just used the reset button to light up one of these LEDs, and then we did an input-output tutorial where we press the button off the board and light up an LED on the board. Excellent. Here is a excerpt of the code for the input-output. The input-output are essentially the same for both. The input is essentially the same for the LED. The only differences is that we declare an input for the button off the board, and here we are shifting the away from 0 to 6 to 7 to 1, and we're assigning the response of LED 7 instead of the reset button to the button we assigned, and the not of the reset for the LED on board.
Alright, so the next thing we did was research a 7-segment display driver, since that's actually what we're using on our board. And this is the schematic we pulled up from online. It's actually one of the logic schematics from an IC. So we implemented this in the schematic viewer of the program on the computer and got it working, got the 7-segment display working correctly, especially with our third subsystem being the inverters, and just wanted to see how that worked so that we could brainstorm other ideas of what else we could do. And after we did that, we got to what our final project is.
So after we figured out how to use the program and what all we could do with the FPGA, we came up with the idea that for our project, and we wanted it to read out on a 7-segment display ELCT-201 Hertz. And we had to create this truth table with the 16 possible inputs from our 4 binary buttons, and then assign to each segment the outputs that we desired in order to create the letters. And then using K-mapping, we created simpler statements as shown above, and then implemented those statements into the schematics for the FPGA in order to have the FPGA itself run through. And there's 7 different sheets, but FPGA is capable of running all of them at once, just in parallel, which is the real power of the FPGA, is being able to implement all of this at one time.
So the troubleshooting we ran into, when we implemented our own design, unlike the 7-segment display driver that we just pulled from online, we needed to invert the ending outputs so that our inverter would work correctly with the 7-segment display. So that was one problem we ran into. We needed to check pin assignments to make sure that some of the segments on the 7-segment display weren't swapped, so we had the right letters popping up, and just corrections in diagrams, making sure our code was correct and debugging our code. And next is the results. So this is our final working project. When the user counts up using binary inputs, the 7-segment display changes letters or numbers based on the truth table we've provided. The driver changes between ELCT-201 space Hertz with a space in the front and at the end. And we can do all this thanks to the Mojo. Alright, so we had success implementing our design. As you saw in the results, we have everything executing what we want to on the 7-segment display. So we got everything working with our design the way it should be.
Some problems we faced during this project was the syntax of the code. It was just between binary and assembly to me. It was very rudimentary and pretty difficult to understand the hierarchy of the programming language until we figured out how to do the diagrams, which made the entire thing much easier.
In the end, we could have done something much more complex if we had had any experience with the coding ahead of time, because we spent the vast majority of our time trying to learn how to use the program. So if we could redo it again, I think we would do something much more complicated, maybe have a mechanical output instead of just lighting up LEDs, have something mechanical connected to it. I don't want to say we wasted our time looking up how to do the code, but it definitely used up a lot of our available time, and it
it was definitely something we could have done better. But that's our project.